This is a talk on our paper about kernelization algorithms for a parameter called C-closure. My name is Tomohiro, and this is joint work with Christian Komasiewicz and Frank Zoma. So let me start with what the C-closure, what a C-closed graph is. So this is a parameter, C-closure is a parameter defined by Fox et al. In ICOV 2 years ago. And it's defined as follows. A graph, first of all, a graph is C-closed whenever every pair of non-adjacent vertices have at most C-1 common neighbors. And we define the C-closure as the minimum integer such that the graph is C-closed. Okay. And the motivation for this parameter is that in real world network, whenever you have two vertices that have a lot of common neighbors, they tend to be adjacent. And in the ICO paper, they also showed that clique enumeration can be done in FPT time. Okay, let me show you some example of C-closed graphs. Well, first of all, a clique can be one closed. Well, actually, it can be zero closed because it doesn't have any pair of non-adjacent vertices. But let me say that a clique is one closed. And if you look at the example on the right-hand side, by clique, k to n is n plus 1 closed because the two vertices on the sides have n common neighbors. So these examples show that C-closure is distinct from some parameters like degeneracy and tree width that sort of measure sparsity of the graph because even in one closed graph, there could be a large clique. On the other hand, a sparse graph on the right-hand side can have a large C-closure. And our results are shown here. So we prove that using this C-closure as a parameter, we can show that several classical graph problems admit polynomial kernels. And in particular, our algorithm is, except for independent set, our algorithm is based on some Ramsey type argument on C-closed graphs. So I will focus on independent set and dominating set for this talk. And let me start with the independent set. So I would like to show you that independent set has a kernel of C times k square vertices. But to show this, we are going to use one reduction rule, which says that when you have a large degree vertex, here large degree means that the degree is larger than C minus 1 times k, then we just remove it. So why is it correct? Let me show you the correctness. Well, first of all, let us say that the G prime is the graph obtained by removing the large degree vertex B. So one direction is clear, like if there's an independent set of size k in G prime, then there must be one in G as well. So let me focus on the other direction, the forward direction. So let S be an independent set in G of size k. And I would like to show that G prime also has an independent set of size k. So there are two cases. The first case is easy. If S does not contain B, then S is still an independent set in G prime. So this is good. So in the second case, when B is contained in S, we somehow need to replace B with something else. So to find that, to show that such a replacement is possible, we use the property of C closure. So due to the C closure, we know that other vertices in S, say U, have at most C minus one common neighbors with B. So it means that since a B has a lot of neighbors, there must exist some vertex in the neighborhood of B that are not adjacent to any other vertices of S. And let's call it B. Let's call it W. Then S minus B plus W is going to be our independent set of size K. So now we've shown that the reduction rule is correct. Let me show you that this gives us a kernel of CK square vertices. So observe that after we do apply this reduction rule, we are going to have maximum degree at most C minus 1 times K. So if the graphs, after we apply the reduction rule exhaustively, if we have a lot of vertices, meaning that delta plus 1 times K vertices, then we can easily find an independent set of size K. So thus we obtain a kernel of CK square vertices. So before I move on to dominating set, let me briefly mention our main technical lemma, which is Ramsey time result on sequence graphs. So Ramsey's theorem says that if you have a graph, if the graph is sufficiently large, it's going to have either a clique of size A or independent set of size B. And let's call such a bound R of AB. So for our purposes, to obtain a polynomial kernel, this result is not so useful because this function R is actually known to be exponential in terms of A plus B. However, on C-closed graphs, we can show that this Ramsey number is polynomial in terms of A plus B plus C. I'm not going to show you the proof, but I'm going to show you how to use this lemma to obtain a kernel for a dominating set. Okay. So to obtain a kernel for a dominating set, it's convenient to consider a more general variant where every vertex is either black or white. Black means that the vertex is not dominated yet, and white means that the vertex is already dominated. So we start with the instance where every vertex is black, and we color some vertices white as soon as we know that it can be dominated. So our reduction rule is going to deal with some cliques that satisfy certain property. So let me say that a clique C is reducible if for any solution, any dominating set of size K, intersection of C and S is non-empty. So such a clique is useful because we can actually reduce it. That's why I call it reducible. Okay, how can it be reduced? So it runs in 4 steps. So consider some reducible clique C, then we are going to do 4 things. First of all, we are going to add a new vertex, call it U, so that it's adjacent to every vertex in C. And then we color each vertex in C white as well as all the common neighbors of C white. So intuitively, this new vertex U is going to ensure that in the reduced instance, the solution must contain some vertex of C. So now I'm going to focus on how to find such a reducible clique. First of all, let us consider a maximal clique that have a lot of black vertices. I claim that such a clique is reducible, meaning that C is going to intersect any solution S. To show this, a crucial observation is that if you look at a vertex outside C, then it's going to have some vertex in C that is not adjacent to it. Well, this is because C is maximal. Now, due to the C closure, we know that this vertex B prime can dominate at most C-1 vertices of C. Well, it means that since C is really large, any solution must contain a vertex of C, which shows that C is reducible. And this reduction, finding reducible cliques can be done in FPT time, because actually all maximal cliques can be enumerated in FPT time, as shown by Fox et al. Large clique of black vertices. Then due to our Ramsey lemma, we know that if there are a lot of vertices, then a lot of black vertices, then it's going to have an independent set of size k+1. Now, let us consider a clique of size c-1 such that common neighborhood D. In the common neighborhood D, there are a lot of black vertices. I claim that such a clique is reducible. So first of all, there is going to be independent set of size k+1 due to our assumption. It means that in any solution S, there must be a vertex in S that can dominate at least 2 vertices of I. And let's call the vertices that are dominated, say U and W. So if B is not in C, it means that U and W are going to have C common neighbors, which is a contradiction. So now we have that S intersects C. There is no clique of size c-1 that have a lot of black common neighbors. Now let us consider a clique of size c-2 such that in the common neighborhood there are more than k times row vertices. I claim that such a clique is reducible. To show that this C is reducible, first observe that any solution must contain a vertex, say V, that can dominate more than row vertices of D. And if V is not in C, because D is an independent set, D is going to contain an independent set, C plus V must be a clique, which means that C plus V has more than row common black vertices. But this contradicts our assumption written above, so this shows that C is reducible. Actually, we can repeat this argument to show that a clique of size C minus I is reducible if its common neighborhood have a lot of black vertices. In particular, this means that for I is equal to C minus 1, each vertex is adjacent to at most k to the C minus 2 times row black vertices. And doing some analysis, we can actually show that dominating this, after doing everything here, the number of vertices is limited by k to the C. In my talk, we've seen some FPGA algorithm or kernelization algorithm for C-closed graphs, but since C-closure is a new parameter, there could be other problems that admit FPGA algorithms in C-closed graphs. Another interesting direction would be to consider the weak gamma closure. Weak gamma closure is defined as like a degeneracy, where we want to ensure that for each induced subgraph, for each induced subgraph, it must satisfy C-closure property. So this gamma is going to be smaller than C, and we actually show that independent set has a kernel of gamma k squared vertices. But other problems such as dominating set, induced matching, redundant set remain unresolved. And thank you for your attention.